Let's have a review from previous session. Previously, we started the axial flow compressor, and we saw the difference between diffuser and compressor there. Also, we started seeing the velocity triangles in axial compressors, and there we came up with relations that were trying to relate the pressure and temperature rise in terms of velocities and flow angles inside the compressor. Then we defined the degree of reaction, and we said that we have some design inputs like the stage loading, flow coefficient, and also this degree of reaction there. So based on these, we can start preliminary design. Now let's see some complementary notes about the axial flow compressors. In this table, you can see the typical pressure ratio, PR, and efficiencies of different applications. Like in industrial applications, we have subsonic flow in compressors, and there the pressure ratio in one stage per stage is something between 1 and 1.2. And the efficiency for a stage is 88 to 92%. While in aerospace applications, we're having transonic flows usually, and these transonic flows are giving more pressure ratios for us, but the efficiency is a little bit lower than these industrial ones. Why is it lower? Because industrial ones are not aerial, let's say, engines or compressors. But in aerospace, you have to pay the price, so you make the compressor as small as possible, as light as possible. That's why your efficiency will decrease. And in research applications, we're having supersonic flows with much higher pressure ratio and again lower efficiencies. And these lower efficiencies are almost because of the losses that occur in the supersonic flow regime. Now let's have a look at the IGVs or inlet guide vanes. As we said, these inlet guide vanes are one stator row at the entry of the compressor, and they guide the air correctly into the rotor of the first stage. So we usually put the guide vanes to come up with the design flow angle at the rotor entry. And because we had some discussion on the velocity triangles previous session, now I want to make it a little bit clear for you. So as we said, these velocity triangles are typically used to relate the flow properties and blade design parameters in the relative frame to the properties in the stationary or absolute frame. So what you see in here, actually, you will see the inlet guide vanes as the first row, right? And then in this part, you are seeing the first stage, let's say, rotor and then stator. So this is the first stage of our compressor. And then you are seeing another stage of this compressor, which is the second stage of the compressor. So you have IGV, then rotor, stator, and it goes on to the subsequent stages. So what we have in here, you see that air is coming like this in axial direction inside the inlet guide vanes, and then this inlet guide vanes actually the air leaves the inlet guide vanes at this let's say direction. So as we said, this is the entry and this is the exit of the inlet guide vanes. So and you have the rotation. So this is the first rotor row of the first stage. So it is rotating, and the direction of rotation is like this, from left to right, it is rotating. And as you can see, this is the axis of the compressor. So you may consider that you're seeing this from the top view of the compressor. So this is rotating, these sets of blades are rotating, so the velocity that the air sees from this rotation is actually the opposite side. So this is the velocity that the rotor blades induce to the, let's say, fluid, to the gas. And as we had mentioned in here, you have absolute velocity, you have the relative velocity, and this u is the peripheral velocity, or this red one in here. So this is actually your, let's say, relative velocity in here. So why we are saying that this is the relative velocity? Because this is a rotor and it is rotating. So while it is rotating, we are facing to the relative velocities, not to the, let's say, absolute velocity. And then you have to assume that this axial velocity that you had in here, it's exactly preserves its magnitude in here. So the axial velocity in the preliminary design is not changing. Whatever comes in as an axial value, it is there after passing the IGV and inlet of the rotor. So this is the triangle at the inlet of the rotor. What is the triangle at the outlet of the rotor? So while the gas is leaving the blades of the rotor, it is leaving like this. Okay, so it is kind of parallel to the tangent of the trailing edge. But again, we are having the rotation in rotor. So this is the rotation in rotor, and this red one is exactly the peripheral velocity u in here. So then again, you have the this vector as your, let's say, velocity, as your absolute velocity in here. So what is done in here? See, this is the absolute velocity, and it is kind of parallel to the tangent of the stator leading edge. So it suggests that we did the triangles right. And again, as I said, your axial velocity preserves its magnitude in here. So if you just put these two triangles uh, like this, you can see that this is the inlet of the rotor triangle, and this is the outlet of the rotor triangle. Now, if you put them on top of each other, you will see that they make such this shape, and there is something in between of these two. This is what we call the change of the whirl speed. So the delta whirl, or change of the whirl speed, is the difference between speeds at inlet and outlet of the rotor. So let's look at these two triangles in much more detail. So we said that this red one is our peripheral velocity u, and then we have the entrance of the rotor as this v1, and we said that this V1 is actually the outlet of the guide vane and entrance of the rotor row. And then it makes this W1, the green W1, as your relative velocity. And this is what your rotor blades are seeing from the air actually. And then while it leaves the rotor, we said that it leaves with this relative velocity. And because we are staying uh, again on the rotor, and we are seeing the rotation, we have this peripheral velocity. So your absolute velocity will be this V2. And we said that this is the delta whirl, or change of whirl speed. So how to determine this delta whirl? If you consider this triangle at the entry of the rotor, you see that you have this angle in here. So this angle is actually your alpha 1 angle. If you remember, the angle that your absolute velocity is making with the axial direction is called alpha. And if you consider this angle and this triangle at the outlet of the rotor, so this is the outlet of the rotor, okay? And this outlet of the rotor, you have the V2 velocity. So we are dealing with absolute velocities, of course, not with the relative velocities in calculating the delta VL. So this is again your alpha 2 angle. So if you know just the axial velocity Vz in here, so if you have the magnitude of Vz, and we said that in the preliminary design, Vz is the same as the speed at the inlet of the compressor. By knowing the angles and Vz, you will know this let's say component of V1 and this component of V2. Then if you subtract the blue one from the brown one, you will come up with the delta whirl speed. Okay, I hope that one is complementary thing. So in this slide, we see some schematic representation of single shaft and twin spool or twin shaft, let's say engines in a single shaft. As you can see, you are seeing these are just examples, and these are just there just to show that what is a compressor look like in a single spool or twin spool, let's say engines. In a single spool, you have your shaft in the center of rotation, and there is a disc that the rotor blades are connected to this disc, as you can see. So, as we said, we have an inlet guide vane, and then we have the rotor and stator. This is a stage 1 rotor stator, a stage 2 rotor stator, a stage 3, and it goes on. And then it compresses the air while it is passing through the rotor and stators, and it goes to the combustion chamber. In a twin spool, let's say it's a turbofan engine, you can see that you have a lower speed shaft, and then you have your high speed shaft. So it is like flow first, the cold flow goes through the inlet guide vane and the rotor and stator of the fan, and then it travels from this place. It's not getting inside the combustor. So this is a fan part, and then we have two compressors, which is the one is low pressure and this one is the high pressure compressor, and these two have different drums and attached to let's say some bearing, and we have different speeds of these, and they are run they are derived actually by high pressure and low pressure turbines as well. So these are just schematics to show you how these are actually put there, the stators and rotors and so on. And then if you remember, we were saying about we were having discussions about the change of the velocity, change of the pressure, static and total pressure and temperature across the compressor stages. And as you can see here, you have two different schematics. Let's have a look at the Rolls-Royce some engine that the Rolls-Royce book gives us. So as you can see, while passing the pressure, you can see the difference of pressure. Pressure is gradually increasing, and the velocity is acting like increasing and decreasing. So the velocity is not changing too much, but it is changing. So you shouldn't just neglect the velocity changes. As you can see, the velocity is changing a little bit. So the pressure, total pressure and total temperature, as we said, are constant during passing the stator blades. As you can see in here, they are not changing, but the rotor has the, let's say, ability to change the total pressure and total temperature. Now let's start our discussion uh, about today's course, today's session. Today's session is about the performance of a single stage. Stage, as we said, is a rotor and a stator in compressor. And then after seeing this performance, we will have uh, to check the map of the compressor, what is the map of the compressor, and then if you remember, we had some discussion on the rotating stall and surge. We will have some notes on these, and finally we will check the effects of the real fluid and the losses there and the mechanisms that generate losses there, and we are finally ending today's session with some examples. So in here, we have, if you remember, we had the psi. Actually, it was our loading coefficient in the previous session, and we defined this psi by this ratio, this relation that is 1 minus flow coefficient times the tangent of the alpha 1 plus axial velocity ratio times tangent of beta 2. If you just plot this psi versus your phi, you will come up with such decreasing, let's say, condition, decreasing function. And in ideal case, it is like a line, a straight line, but in real case, it is like this curve. So it doesn't matter if you just plot the pressure ratio, which is P02 over P01, over corrected mass flow rate or mass flow parameter, m dot the square root of theta over delta. These are defined before, if you remember. So theta is your temperature, uh, temperature ratio. You will come up with such curves. Okay, so this is for a single stage, and actually this loading coefficient. This question might comes into your mind that why do we call this as loading coefficient? What does it mean, loading? Because you remember that when you have airfoil, when you have lift of this, it means that the load on the airfoil uh, is the lift force, right? So the loading coefficient is directly related to the lift. And in here, we showed that how is it directly related to the lift. Because if you increase your angle of attack, beta, it means that the beta angle for the rotor is increased. It, and you remember that if you increase the angle of attack, normally the lift is increasing until some point, and then it is stalling. So the lift increases as you increase the angle of attack. When the lift increases, so the torque that the lift is generating is increased. And when the torque is increased, we know that torque and power are related. So the power is increased. And when the power is increased, it means that your loading coefficient is increased. And how do we actually increase the angle of attack? If you just decrease the phi, and you remember phi was the ratio of axial velocity to the peripheral velocity. So if you just decrease this, it means that you are changing your angle of attack, you're increasing your angle of attack. So let's have a look at three different conditions. The first one is the design condition, when your phi or Vz over u is the designed value of your phi. So at this place, as you can see, you have beta 1, which we said that this is the angle between relative velocity and the axial direction. So you have this beta 1. The flow comes like this inside and leaves like this. So your W is actually decreased. But if you take a look at a different case, which we call it as off design condition, we're going to have two different conditions actually. One is that if your, let's say, flow coefficient, this phi, which is your flow coefficient, is smaller than the design value. And this happens normally in such cases as we put in here, when the aircraft is steep turning, or when it is at takeoff and landing, especially for fighters. So this condition happens for this. Um, your flow coefficient, is phi, which we defined Vz over u previous session. Your flow coefficient is less than the design amount. Now let's compare, let's say, this triangle to this triangle. So this triangle in here, in the second one, the flow coefficient in here is less than the design, right? That's why we are having a steep, let's say, vector of the W1. When it is steep, it means that it has angle of attack, a higher angle of attack. And higher angle of attack, it means that the flow can separate from the leading edge. And when it separates, you will have a stall, right? So in this condition, to 1, your Vz is reduced, so your mass flow rate is reduced. Why mass flow rate is reduced? You see, this is separated, so it's acting like a wall, so not enough mass can pass through this wall, right? When the mass is passing, not enough mass can pass through this wall, and some of it can come back. So this may lead to the flow separation. And how do we manage this? Actually, if you can just rotate the blades, then you can manage it. And when you rotate the blades, that's what we call variable angle stators, or IGB. So just imagine that if you can rotate this blade a little bit more like this, so then if it is rotating like this, then you can manage this stall and flow separation. Now, this is the first condition in the off design conditions. The second is when your Vz is increased. So when Vz over U is uh, greater than the design value, so what happens in this case? In this case, you can see that it is not steep anymore. So actually, it is happening in a steep dive maneuvers. So what is happening? Flow can separate from the bottom side of the blades, bottom side, or the pressure side of the blades. That means that you will come up with some negative angle of incidence or negative angle of attack in the blade, and then flow separates from the bottom side. How do we manage this one? We can manage this one by some controllers in the flow, like the blow-off valves. So the blow-off valves will take the excess amount of air outside. So when you take the excess amount of air, it means that your VZ will be smaller. And when your VZ will be smaller, then you will end up with a smaller W as well. Okay, now let's have a look at a compressor map. You will usually see these maps for compressor and turbines. What is a compressor map? It's actually a chart created for a compressor in a gas turbine engine. Complete maps are based on compressor rig test results or predicted by a special computer program. Alternatively, the map of a similar compressor can be suitably scaled. So this is the beauty of the similarity. See, the similar compressor can be suitably scaled. So when you have a map generated for some compressor, and when you just express some non-dimensional values like the pressure ratio, not the pressure itself, okay, to versus equivalent, relative equivalent flow, okay. So this is actually your expressing your mass flow rate. So this is not only m dot, but it is expressing your mass flow rate, and these are the different, let's say, RPMs of this compressor. We will see it in a second. When you're defining all the things in a non-dimensional uh, values, non-dimensional numbers, you can suitably scale them. So these compressor maps are an integral part of predicting the performance of a gas turbine engine, both at design and also off-design conditions. Fans and turbines also have operating maps, although the latter are significantly different in appearance to that of compressors. So you're seeing a sample of compressor map in here, but for a turbine map, you will see it in an axial turbine part actually, but it is much different than this. While you are reading the literature, you may come up with this E3. So this E3 means energy efficient engine. As we said, the compressor map is a diagram of psi versus phi, or as we said, equivalently pressure ratio versus our mass flow parameter, which is m dot square root of temperature ratio over delta. Delta is our P over ambient pressure. Why we are generating this map? We said that because we cannot do ground test and then apply the results to the flight case. And this, we said that this is the beauty of the non-dimensionalizing. We just non-dimensionalize everything and then we generate this map. And when we generate this map, we can scale this to an actual real case compressor. So in this chart, what we see actually, this is a very important thing. So please just give attention to this. You are seeing the pressure ratio of compressor plotted versus your mass flow parameter. Okay. And then just like the real, let's say, plot in here, this is a real case. Okay. In here, we have the typical plot. Just as in a real case, you're seeing some curves like this. Okay, let me show it by laser pointer to you. You are seeing some curves like these curves. So what are these curves? These are actually the corrected RPMs. What is a corrected RPM? It is RPM over a square root of theta. Theta is T over T ambient. So at different revolutions of this compressor, they are changing the mass flow parameter and they are checking the pressure ratio of the compressor. Okay, so let's say compressor is rotating at 500 RPM, is corresponding to this, let's say. Then at this 500 RPM, they are changing the mass flow rate. Okay, this is done by changing the by just putting some barrier at the back of the engine or back of the compressor, so then they can adjust the mass flow rate. Whatever comes in cannot go out. So the mass flow rate is changing, is decreasing or increasing. So by changing the mass flow rate, they are measuring the pressure ratio, and then they are drawing the curve, the first curve. Then they are changing the RPM of the compressor and do it again and again and again. So what will happen? You will see that at each RPM, after changing at some mass flow rate, you cannot actually see that when you reach to some mass flow rate, you have a lower limit. What does it mean? It means that actually you cannot change the pressure ratio if you increase the mass flow rate anymore. So it's a vertical line. Vertical line means it is your limit, it's the end. So that's where your compressor is actually choked. So there is no more chance to give more air or more gas inside this compressor. And there is actually another limit on these, and you see this upper limit as we call it as target stall line or CL max. This is where the compressor stalls. So this is where that your uh, actually flow inside the compressor is not anymore attached to the blades and it is stalled. So what you are doing actually is to checking this core engine operating line, where you have reached your actually maximum mass flow rate, and the target stall line we have where we have maximum coefficient of lift, and then you put your design point in between of these. So for example, I put my design point in here. So this is the region that I'm safe while designing my compressor. Uh, yeah, in here you can see the mass flow parameter is a function of the Mach number and your gamma. When your Mach number is 1, when you have a choked flow, it means your mass flow parameter will be constant. So if your mass flow parameter is constant, it means that your mass flow rate is maximum there. So this is very important. That's why I'm insisting on the compressor. We have a flow axis or a pressure ratio axis in compressor maps, two different compressor maps. In the flow axis, as you can see, the x-axis is usually some function of compressor entry mass flow, usually corrected flow or non-dimensional flow, as we said, mass flow parameter, as opposed to real flow. This axis can be considered a rough measure of the axial Mach number of the flow through the device. So actually we said that it is a rough, when we say it is a rough um, measure of the Mach number, we are actually aiming this. So when we have choked flow, your Mach is 1, so your mass flow rate is maximum. And the pressure ratio axis in here, you have the pressure ratio where P0 is the stagnation, and delta T over T, where T is the stagnation or total head temperature, is also used there. And as we said, we have this stability line, or what we said, target stall line in here. We have a working line in here. What is working line? We will tell it to you. And this is the lower limit is the actually we had this lower limit as the core engine operating line, which is the bottom constraint. So as you can see, there are these curves are we said that these are the line of constant rotational speed, or n over square root of theta, and you see that after these they will become vertical, so there is no need to plot them, and you can see that the nd represents the design RPM. So when we say 0.5 nd means that we are at the half of the design RPM. For example, if the compressor is working at 30,000 RPM, this curve represents 15,000 RPM for that compressor. Okay, and as you can see, we have values a little bit higher than the design RPM as well. So 1.05 design RPM is also there. Okay, let me stop this video for some minutes, and then again I will record the rest of the session. Okay, let's continue. In this map, we are showing some stuff, which is the first one is the surge line. So this surge line is the slightly kinked diagonal line on the main part of the map, which we said that it is a stall or surge line. And we said that above this line, on an unstable region or unstable flow region is actually does exist, and we are always avoiding to be in this let's say region after surging of the compressor. A compressor surge typically causes an abrupt reversal of the airflow through the unit as the pumping action of the air follows the stall. So when it surges, it is making some noise, and it is like shaking. Also, we have a surge margin in here. As the name suggests, surge margin provides a measure of how close an operating point is to surge. So you remember the point that I showed you in here, the design point or operating point. And this is an example of that design point or best efficiency point. There are a number of different definitions of a surge margin. So a popular one, surge margin is defined as this. So as your surge margin is actually the difference between mass flow at the operating point and mass flow at the surge at same corrected speed as mass flow in operating point, and it is actually described in percent. As you can see, this is the surge margin for the this kind of, or let's say this special kind of compressor in here. And we said that we have speed lines. So those curves, those RPM lines, near vertical lines on the main part of the map are the constant rotational corrected speed lines. We said they are a measure of rotor blade tip Mach number. So at each, let's say, rotation, you have at the tip of the blade, you have some Mach number, and these are actually measured, a kind of measure of that Mach number. The operating line, which is a working line, is a typical steady state working line. And this is a locus of the operating points of the engine as it is throttled. So what is it? This operating line, this blue line, actually you can see that these are the locus of some points. These are the locus of different best efficiency points at different RPMs. When you are just putting all these points and attaching these points together, you'll come up with a line that you'll call it as your operating or working line.